Hey guys, I'm back with a new video. So in the previous video we learned about what is simple linear regression and I gave a brief introduction about it. Now let us discuss about the data set that we will be working with for our linear regression exercise, and let us understand the features or the input variables given to us and the output variable that we have to predict for. And then we will discuss about something called as the residual sum of squares in case of linear regression. So let me show you the problem that we will be working with. So let me zoom this a bit. Okay, so we'll be working with Old Faithful Geyser dataset, and in this problem basically you have to predict when will the next eruption occur. So we are given a natural geyser and you are given input variables like the waiting time between eruptions is your input variable. Between two successive eruptions we are given the waiting time and the duration of eruption for the Old Faithful Geyser in Yellowstone National Park. So we are given a data set with 272 rows on two variables. So your input variable is basically the eruption time in minutes and waiting time to next eruption. So we basically have to find the interval after which the next eruption will occur. So this is your output variable. Okay. So in this problem you basically have to predict when will the next eruption occur. So we have to generate a machine learning model to predict for interval variable given a new unforeseen value of the duration variable. Okay, so we will have two variables, duration and interval, or you can say eruptions and the waiting time or the interval after which the next eruption is bound to occur. So this is all about our dataset that we will be working with, and as per the conditions discussed above we can apply the simple linear regression model here because we have a single input variable, as you can see. Okay, and these are our serial numbers, so it won't go into our analysis. Okay, we are having eruptions and we are having waiting. Okay, so we will rename that as, this will be our duration for each eruption, and waiting will be renamed as interval after which a new eruption will occur. Okay, after how much time a next eruption is bound to occur. So this is what we have to predict for. So we will apply simple linear regression model here, of course, because we have only a single input variable with us, which is the duration, based on which we can model our output variable. Now one thing must be arising in your mind is that how will we determine the parameters of our model, the coefficients that we had discussed about in the previous video. So now using the training data and the learning method, which in our case is simple linear regression, you have to find the values for parameters of the model, which are m0 and m1. So let's go back to our whiteboard and discuss about this. So I'll clear my screen. And let us understand the concept of scatter plot, which demonstrates the relationship between input variable and the output variable, which are both continuous in nature in case of simple linear regression. Now once you have the scatter plot for a dataset ready, then let us draw the line y m0 plus m1x, which is our linear regression line. So say it looks something like this, and then you have your dataset points. Okay, so these are our dataset points and this is our model, this line. Okay, now this is basically passing through the coordinate density region or your point density region that we have got. Okay, so it must be passing through some of the points, and most of the points it is possible that it might not be passing through all of them. So this line will represent a model, and we have to determine the values of m0 and m1, which are the parameters of our model. We don't want any random line and make it fit our data. We want a line that can exactly represent the relation between our data. That is a line that fits the data as closely as possible. Okay, so we have to find a line that represents our data as closely as possible. So a line that fits the data as closely as possible. But how do we represent the relationship of our data set or the proximity of the coordinate density to our line? Okay, so we have to estimate how close or what is the proximity or how near these points are with respect to our model equation or with respect to our line that we are having. That is a major question that arises here. Now here comes the concept of error, which we will see more in coming videos as well, but let us apply it here for our present case. Now for every prediction there will be some error, okay? Some error element will always be there for every prediction. So that is what you need to understand. Now let me show you this in the diagram. Now let us say for a specific value of x, let us say this value of x. So for a specific value of x in our data set, we have a value for say y value. So let us say this is your value and this is your value, okay, for a specific value of x. So we will have a value of y. Let us see what the model shows the value of y for the same value of x. So the model will show this value for the very same value of x. So this is the value that is predicted by the model, and you can term it as say y cap, and this is the value that is already described by the data set, okay, for the same value of x. Now to find the error between the real prediction done by the model, which is, as I already told you, y cap, this is the real prediction that is done by the model, and the output variable that we had from our data set for the same value of x, which is this one, okay. So this is the difference that we are looking for, and this is basically termed as error. So error is observed value, so observed, or you can say real value, minus the predicted value of your model for the very same value of x. So predicted value for a model, okay, or by your model. Now this difference is known as error. The error element will always be there for each and every point of your data set. So here also, if we take this as some value of x, say x2, and the predicted value for this very same value of x by the model be say y2 cap, then here also we have some error as this error, okay, and here this is your error, and even error can be like this. So this is your error when for a certain value of x, say x3, the data set says that the value for y should be this, say y3, and the model says that the predicted value should be y3 cap. Then here error will be this, okay, this difference will be the error. So we can have errors for all the values of your data set that we are having will be there for each and every point of our data set, as you can see from the graph. So the only thing we can do is to reduce or minimize it as much as possible, though we cannot eliminate it completely. Now we compute something called as residual sum of squares. So residual sum of squares. Now remember that error is also known as residual. So whatever you are getting like this difference is a residual, and this is also residual, okay. The difference between your observed value, the real value that is already described by the data set, and the predicted value that is being described by a model, okay. So RSS, you can term it as RSS or residual sum of squares. So we can say this as even square, okay. There are due to the very first point, so let us say this as x1, and then we will have for other points as well that are there in the data set. So there may be positive difference like for this case, or there may be negative difference like for this case, okay. but we are interested in the magnitude of the error, okay, and not the direction or not the sign of the error, just the magnitude. So I can say residual sum of squares as even square, e2 square, e3 square, and let us draw a simple manual diagram for understanding this. So we can say this, and then let's say this, this, this. So these points, these lines are representing the differences between the real value and the predicted value, and any point on the line is representing the predicted value. And these points, like this one, or this one, these are representing your real values, okay, that are described by the data set. So we are interested in the differences that we are getting, these differences, okay. So I can term this difference as even for the very first point. This is e2, e3, and so on. So e3 square, e4 square, e5 square, to say n such points, so en square. Now I can say as even as if we use this formula, so observe real value, which is the real value described by your data set for a certain point. So I can say this as y1 minus the predicted value. The predicted value is basically the one that is lying on the line, okay. So that is, say, y1 cap, as I already told you, plus, and we can continue like this, y2 minus y2 cap, y3 minus y3 cap, and so on till yn minus yn cap whole square. So y1, y2, y3 are your actual values that we had in our dataset, described by our dataset, and y1 cap, y2 cap, these are the values predicted by the model, okay. So let me clear up the screen and let us move forward. So we can say y1 cap, the predicted value for the very first point in our dataset, as m0 plus m1x1, okay. Using the equation of the model that we had, we are plugging in these values, okay. The x1 is your input variable and y1 is your predicted value, okay, and not the real value described by dataset, as I discussed. So we can minimize, or we can basically describe our RSS as y1, and plugging in the value of the predicted value, we can say m0 plus m1 x1 and whole square, plus for y2 we can say again m0 and m1, which are our parameters of the model, and x2 whole square, plus, and keep on continuing this till yn minus m0 plus m1 xn and whole square, okay. So our main goal is to estimate the value of these parameters, which are m0 and m1. So on solving this in the final form, this comes out to be, so m1 comes out to be summation, okay, from summation from k1 to summation from k1 to n. So I'm summing up all the values and I say xk, so a certain point xk, which is a certain input variable, minus x bar, which is our mean value of x, I will tell you shortly, and then multiplied with yk minus y bar divided by summation from k1 to n and xk minus x bar whole square. Now here xk is the value of your input variable of the kth row of your data set, okay. So if I assume this to be our data set, and let us say this is our kth row, the kth row of our data set, so xk is your value of the input variable of this row, okay. Yk is the value of output variable of the very same row, so this can be yk, say this is your output variable, and this is your xk, the input variable that is pertaining to the kth row, okay. So x bar and y bar, which are these are basically your mean values that you are taking the average of all the columns that are represented, average of all the values under the columns that are represented under the head x and y, okay. and your m naught comes out to be y bar minus m1 x bar. So do take a note of these formulas because we will be using them later as well. Okay, so these are very important to take in mind. Now let us start with the implementation in the very next video. I guess this video took a bit longer to cover about the problem that we will work with, but we discussed completely about how we can estimate the parameters of the model. So in the next video, we'll learn about the performance metrics for evaluation of our machine learning model. Let's catch up in the next video.